Hi everybody, my name is Kevin Moore. I'm a grad student at UCSB doing research in astrophysics, and I'll be teaching a course for SST in the fall called Juggling Space and Time, Einstein's Relativity, and I hope you'll join me this fall. So our story for relativity starts out with a boy in high school, probably not too much unlike yourselves. So Einstein, when he was 15 and 16, was bored in school. He was not a good student. His teachers would often send him home with notes telling his parents how destructive he's been. His parents were on his case about trying to get into a good college and making sure he has a good career. But Einstein wasn't caring about any of this. Einstein was worrying about a question about fundamental physics. He was wondering what it would look like if he were to ride on a light wave. And it turns out that the answer to this question revolutionized our notions of space and time. And so, what is light? What was known about light when Einstein was a child? It was known that it had a speed. It was very, very fast, but it had a finite speed, 186,000 miles per second. That's fast enough to get from the Earth to the Moon in about a second. But it wasn't really known who measures this speed. There was no mention of what reference frame this speed was in. So do you measure it in the frame of the Earth? Well, the Earth's spinning, and the Earth's also rotating around the Sun. Do you measure it in the Sun's reference frame? That would seem more natural, maybe. Well, the Sun's also rotating around the center of the galaxy. Do you measure it in the galaxy's reference frame? Well, no one really knew what reference frame was the chosen reference frame of this speed. So that was one small problem with light at that time. It also has both wave and particle properties. And so, unlike sound waves, which travel through air, and water waves, which travel through water, it wasn't really known what light propagates through as a wave. It seems to have no trouble propagating through a vacuum on its way from the Sun to the Earth. So that was another problem with light. And so the fact that light didn't obey the same laws as matter. So matter obeys what's called Newtonian mechanics. And so these are the laws that govern baseballs, cars, giraffes, everything that you are familiar with in the material world, except light. And so light obeys its own set of laws called electromagnetism. And so the fact that they don't obey the same laws and that these laws are somehow subtly inconsistent with each other was a small problem for physicists at the time. Now, most of the older physicists thought that this was just a small problem that would go away soon. But the problem that Einstein was thinking about was actually a very important scientific problem of his time. And so the way that he solved this problem actually revolutionized our notions of space-time. And so it turns out that space is not a fundamental static entity. Time is not a fundamental static entity. Space-time is woven together in such a way that it's the fundamental entity of the universe. And so this leads to lots of weird effects. There's length contraction, so things that are moving really fast appear to be squished along the direction of their motion. There's time dilation. Things that are moving really fast appear to have time move slower as compared to your clock. And we'll talk about all of this in great detail in the class. So this is also a great example of extraordinary claims requiring extraordinary evidence. So the evidence that supports relativity comes from all aspects of physics, pretty much. It comes from things like atomic clocks, the GPS system, particle accelerators, various aspects of astrophysics. And so we'll go through lots and lots of the evidence that we have for relativity, what kind of experiments gave us those evidence, and why that evidence is trustworthy. And so we'll spend a lot of time in class discussing the role that evidence plays in scientific theory. Lastly is general relativity. So at the end of the class, we'll talk about how Einstein reformulated his theory of relativity 10 years later to include gravity. So now not only is space and time meshed together into space-time, but it can warp. And the manifestations of this warping is general relativity. And so the manifestations of this warping gives us gravity. So you can get all sorts of weird, exotic things in astrophysics like black holes, wormholes, warp drives, all of these weird theoretical constructs that we'll talk about. So why would you take relativity? It's one of the modern pillars, or major pillars of modern physics. And so not knowing about relativity is sort of like not telling you the final the ending to a story. So if you learn about normal physics in high school, you might want to know what comes next. Well, relativity is one of the things that comes next. So physics is not just about studying the mundane and the everyday, the stuff about everyday life. It's also about examining the things that are unfamiliar to you and finding out the laws of nature in such an unfamiliar realm of the very fast and the very large can be very exciting. And so it's also a great illustration of the process of science, how simple ideas and evidence can eventually overturn notions about the universe that were held for centuries. And so it's a great example of how science actually works in the real world. So what will we do in this class? It's going to be a discussion-based course. We'll talk about the nature of space and time, matter and light. We're going to examine the evidence for relativity. There are tons of paradoxes that crop up when you're learning relativity that we can discuss and go through. We'll do some calculations. There will be math in this course. We'll calculate how time slows down when things are going fast, how lengths contract, and at the end we'll talk about general relativity and all of the exotic things it predicts. So black holes, things like gravitational lensing and gravity waves. So again, my name is Kevin Moore. The course is Juggling Space and Time, Einstein's Relativity, and I hope you'll join me in the fall.